Guys, today we're going to take a look at how to solve polynomial functions using graphs. The later part of this notes, which you'll see later in the week, will be how to solve them using tables. We're going to focus on the graphs for today. So if you remember, the last thing that we talked about, and one of the first things that we talked about in this unit, was something called the fundamental theorem of algebra. So that fundamental theorem of algebra says that whatever the degree of our function happens to be, that will be the number of zeros that we have. So if our degree is 10, we should expect to have 10 zeros for our function. This total includes both real zeros and imaginary zeros. Okay. Real zeros we can see on the graph, they look like x-intercepts. Okay. So if I want to find the real zeros of a function, I can take a look at the graph and see where those x-intercepts are. So as we take a look at the graph of our first function, which I have over here, over here for us, I can see there's x minus 2 squared plus 1, and then I'm going to go ahead and menu, analyze graph, 0, find those x-intercepts, right? That's why it's called 0 on your calculator when you go to find those x-intercepts, because those are the real zeros of your function. So let's find the other one here. So I've got x-intercepts at -1 and +2. So real zeros are -1 and +2. And then I want you to notice, we talked about this with the fundamental theorem of algebra. I want you to notice that this x-intercept here at +2 has quadratic behavior. That means it counts for 2. So I'm actually going to list it twice here. This 2 is not any different than this 2. That just sort of helps with our total number of zeros as we're making sure we have all the ones we're supposed to have. So I would expect this function to have 2, 3. It has a degree of 3, so I would expect it to have 3 total zeros. I have 1, 2, 3 real zeros, accounting for that multiplicity. That means that I would expect to have no imaginary zeros there. Let's now take a look at our next problem. X squared plus 3 times x minus 4. I've got this pulled up for us here. X squared plus 3 times x minus 4. Just one x-intercept on this graph. We have a real 0 at 4. That's linear behavior. If it were cubic, that would count for multiple, or if it were quadratic behavior, that would count for multiple. But linear behavior here means I've just got one of those. Now, my degree for this function would be 2, 3. So that means I'm going to have some imaginary zeros here. If I've got one real zero, that means I must have 2 imaginary zeros. Okay. And actually, if we just take a look at the graph, if I take a look down here, we'll talk more about this in a few minutes. But notice that I've got sort of crazy stuff happening on my graph away from the x-axis. We'll talk more about that a little bit later. So when we find zeros of a function by looking for x-intercepts, they're called zeros because what we're actually looking for is what's the value of x that makes the y value, makes the function value 0, right? That's an x-intercept when the y value is 0. And when the y value is 0, we say that the function value is 0. So this is why we're able to use those x-intercepts to help us solve our polynomials. So as we look at solving, here I asked you for the zeros of the graph. Now I'm telling you to solve. I'm asking you for the same thing. So if we're going to solve this equation by graphing, this is the first one this is the same one that was our first example, right? So if I'm asking you to solve this equation by graphing, I'm asking you then to take a look at that graph and tell me where are the x-intercepts, right? What are the values of x for which the function value would be 0? My real solutions would be -1 and 2. Remember that 2 has a multiplicity here that we have to account for. Quadratic behavior means I'm going to go ahead and list that one twice. That way our degree of 2, 3 matches our total number of solutions, and we can see we would have no imaginary solutions there. Okay, so same idea. I'm looking for those x-intercepts. For my next function here, if I take a look at my graph of 2 times x squared plus 1 times x minus 2, again, I'm looking for those real solutions. That means I'm looking for those x-intercepts. So I have an x-intercept here at +2, and then my degree would be 2, 3. That means that my real solutions, right? This is linear behavior. It's not cubic or quadratic. There's no multiplicity I need to factor in on this one. That means that I would have to have some imaginary solutions. If I only have one real solution, I should have three total. That means I've got two imaginaries. Again, I want you to notice I see some sort of goofy stuff happening in my graph away from the x-axis. We'll come back to that in a minute. Let's take a look at our next example, negative x cubed. So negative x cubed plus 7x squared minus 7x minus 15. Here's my graph. My degree here, we've got standard form, so I just look for the biggest exponent. My degree is 3, and my real solutions would be those x-intercepts, so -1, 3, and 5. I have 3 real solutions here. That means no imaginaries. Then let's take a look at our last graph. X minus 4 squared plus 3. We've got a great example of vertex form here. Excuse me. Now remember what we're looking for, those x-intercepts, okay? I'm looking for when that y value is 0. This guy doesn't have any x-intercepts. It's a parabola that's vertex is above the x-axis and it's opening up, so it's going to continue up forever, but it's never going to touch the x-axis. So I have no real solutions. That means since my degree is 2, I would have to have 2 imaginary solutions. Okay? Now, for this last question, what do you notice about the graphs of the functions that have imaginary solutions? Okay, so here we have a parabola that never touches the x-axis. If I flip back to one of my earlier problems, this example right here that had, we said imaginary solutions. I've got this curvy stuff happening away from the x-axis. So anytime I've got, and if I look back at one of my other earlier functions here, this guy, we said would have imaginary solutions. Again, curvy, wiggly stuff happening off the x-axis. What do you notice? So either the graph doesn't touch the x-axis at all. So one option is the graph doesn't touch the x-axis, like our parabola that opened up and was above. Or my graph, the graph has some sort of bumps, dips, wiggles, whatever we want to call them, some kind of stuff happening off of the x-axis. That occur off of the x-axis. Okay? So that means that I can actually look at a graph and decide if I would expect it to have imaginary solutions based on if these things happen on my graph. So if we take a look at the next page, page 9, okay, which graphs below indicate imaginary solutions? So I'm looking for weird stuff happening away from the x-axis. If I take a look at A, pretty standard parabola, right? I've got my vertex there. I notice that it's a little wider than normal, but the sides go out at the same rate. So it looks like we're going down 1 and over 2 to get to those next points. And I keep that consistent sort of widening pattern. Nothing fancy, nothing crazy, nothing imaginary happening there. But if I look at B, I've got bumpy, wiggly stuff happening off the x-axis. So I would expect B to have some imaginary solutions. If I take a look at C, same idea. Bumpy, wiggly stuff happening off the x-axis. Okay, so I would expect C to have some imaginary solutions. And then if we take a look at D, D is a little tricky because it looks like a parabola, but I want you to pay attention to how it grows, how it widens. Okay, so there would be my, what I want to call the vertex, because again, it looks like a parabola. But if I look on this side over here, if we go up 1, 2, 3, 4, and up 5 over 1 to the next nice point, I would expect to be able to do the same thing and get a nice point on this side as well. So if I go up 1, 2, 3, 4, 5, and over 1, that symmetry doesn't hold, right? Not symmetric. Since I'm not symmetric here, that means this isn't actually a parabola. And again, I would expect some imaginary solutions there, okay? So I can't tell exactly what those imaginary solutions are from the graph. I don't know if this has imaginary solutions at 2i and negative 2i, or 1 plus 7i and 1 minus 7i. I don't know. I can't tell that from the graph because I don't have imaginary numbers on my xy axis. But I can tell that there are some imaginary solutions, okay? So from a graph, we know we can tell the x-intercepts, right? I can also look at it now and decide if it's also going to have imaginary stuff. And then the last thing I'm going to talk about is for our functions over here, we had them equal to 0. And that was great because 0, right, is that x-axis. When y is 0, that's the x-axis. So I'm just looking for x-intercepts. But when I'm not equal to 0, if my function's equal to negative 2, or x minus 2, or something even more complicated, how can I find my solutions there? Do we have to move everything to standard form? Am I going to have to distribute this out and combine my terms? The good news is the answer to that is no. We can actually just graph what we have here. So what I'm going to do is graph each side of my equation. So if I go over to my graph here, and let's go ahead and add a page. Let me pull this over. So Control Doc to add a page. Let's add a graph. And then I'm going to scoot this over again so we can see our, oops, sorry guys. Scoot this over so we can see our function. I'm going to graph the left side, which would just be negative 2. So negative 2. Hit enter. Then I'm going to hit the tab key to bring up that function line again. And then I'm going to graph the right side of this. So that would be x cubed minus 7x plus 4. And hit enter to graph that side. And then what I'm going to look for are the x values at my intersection points for those two graphs. Okay, just the x values. I don't want the entire ordered pair, just the x values. So to find that, I'm going to go to Menu, Analyze Graph, and this time I'm looking for intersections because I want the spots where those two graphs that I made intersect. And just like with our zeros, we have to find them one at a time. So my x value there is negative 3. And then let's find another one. Menu, Analyze Graph, Intersection. Here's another one at, looks like positive 1. And then let's find our last one. Menu, Analyze Graph, Intersection. And there's my last one at positive 2. So those are my real solutions, my intersections on the graph. My degree is 3, and I have 3 real solutions. So that means I would not expect any imaginary solutions here. I don't have any imaginaries, I have all real solutions. Okay? Same idea, even if it's not just a single number. Okay, so let's take a look. Control Doc, let's add another graph. And let's graph this next guy. So x minus 2 is the left side. And now we'll hit the tab key to bring up that equation entry line. And this time we have negative, make sure you use the negative key, not subtraction, negative x plus 1. And this guy's squared. And we'll hit enter. And now I'm going to look for, again, those two intersection points. So Menu, Analyze Graph, Intersection. There's 1. And again, remember, we are just wanting those x values. So negative 3.3. And then Menu, Analyze Graph, Intersection. There's our other guy, 0.303. Our degree here is 2. Even if I move this stuff over and distributed this out, I would still get an x squared as my biggest exponent. So I've got two real solutions. That means we would have no imaginaries. And then we have a similar idea over here, right, with our next example. Oops, scoot that over. The only difference is this time my parabola part, right, that x plus 1 squared, doesn't have a negative in front. So I'm actually just going to keep this same graph and then edit it. Get rid of that negative and see what we have going on now here. Now that negative in front made our parabola open down before. Since I'm positive for my lead coefficient for that parabola, this time it's opening up. I want you to notice as we're opening up, I don't get any intersection points. My line is going to keep chugging on this way. My parabola is going up forever, and then going up forever, but it's missed its chance to intersect with this line. So I'm actually not going to have any real solutions here. Now our degree is still 2, right? The only thing we changed was that sign in front. So I would still expect 2 solutions, but this time they're both going to be imaginary. Because those graphs don't intersect, that means I'm going to have 2 imaginary solutions for that one. Sounds kind of crazy. Now the last example we're going to look at for today, we've got an x squared thing over here. And then on this side, my degree would also be 2. If I were to distribute this and combine all my like terms, I'm still looking at a degree of 2 here. So that means I'm going to expect 2 solutions. Let's go ahead and add a page, new graph, and graph this thing. So 5x squared, graph that. Really sort of narrow parabola there. And then we have our other, I would expect this to look like a parabola, right? Because it's an x squared thing. X plus 1 times x minus 3. Graph that guy. And we've got 2 parabolas with sort of different widths here. So one sitting inside the other. Now they're not perfectly lined up. Those vertices are offset from one another. But I want you to notice that my pink parabola here, purpley pink parabola here, is like that standard width of 1. And my black parabola sitting inside is much, much narrower. So what I want to know is, are they ever going to intersect? Well, we can adjust our zoom here. So zoom, let's zoom out a little bit and see what we have going on. So make this the center. And you can see that as far out as I'm zoomed, we always have that pinky purple parabola on the outside and the black parabola on the inside. And if I continue to zoom out, so this is at 1,000 on the y-axis, I still can see very faintly that pinky purple parabola on the outside with that black parabola on the inside. So this is another example where we're going to have no real solutions, which means since my degree is 2, I would expect 2 imaginary solutions. Okay? So if I want to solve by graphing, we can look for x-intercepts if my function is set equal to 0, right? Like we did on the last page, on page 8. I also know, based on the shape of my graph, if I'm going to have imaginary solutions or not. So if I've given you the graph, you can tell where your x-intercepts are, and you can tell me if you're going to expect imaginary solutions. And then if my function isn't set equal to 0, if I've got it sort of split across that equal sign, we can graph each half of my function and look for those intersection points to determine where my solutions are. Okay, that's it for today, guys.